Liquid-liquid extraction is a common practice that chemical engineers use in industry to separate solute from one liquid phase into another. And the two liquid phases that we work with are commonly referred to as the solvent phase and the carrier phase. And we will be moving a solute from the carrier phase into the solvent phase. And the way this works is there will be some kind of concentration difference between the two phases, and that acts as a driving force for mass transfer. And our solvent will have a higher miscibility. It can solvate more of the solute than the carrier phase, which also assists in the mass transfer process. And so on a process flow diagram, what we will have is a series of trays that act as contactors between the two liquid phases. So to draw this out, what we would have is something like this, and we could extend this on indefinitely. We will have some kind of, so I will do ... and then 2 in some kind of stage n. We will have a solvent entering our stage here and leaving our first stage or contactor. We will have some kind of extract, E1. This will be our first tray. And leaving our second tray, we will have an extract with some composition E2. And extending this to our nth tray, we will have a outlet extract composition En. And then coming in to our nth tray, what we will have is a feed with a known composition F, and the feed will continue to move in a countercurrent fashion through our liquid-liquid extraction unit, and leaving our first tray, the tray that our pure solvent enters, we will have some retentate composition referred to as R1. And we can say the same of the trays preceding it. So in this case, R2 will be leaving tray 2, and R3 will be leaving tray 3. And this final value will be R sub n. And the way this works is we will have our solute A present in the feed, and our feed is, and then we'll generally make this assumption, entirely carrier plus solute, and the solute will move into the solvent phase here. And the reason we generally will operate liquid-liquid extractors in a countercurrent fashion instead of a co-current fashion is because this maximizes the concentration difference at every single stage in our unit. We will have our most concentrated extract interfacing with our most concentrated feed, and at the other end of our liquid-liquid extractor, we will have our least or most dilute retentate contacting our most or our least dilute solvent. And so this is a way of maximizing the concentration profile within our system to maximize efficiency and minimize the number of trays that we will need. And so a common question that we are asked in chemical engineering classes is how many trays will be needed if we are given F, which is the feed flow rate, or molar flow rate. Sorry. Damn it. feed flow rate, the solvent flow rate, the feed composition, the solvent composition, and the required retentate composition exiting tray N. We can tell someone the number of trays required, which is equivalent to our variable N in this system. And a quick note before I get into ternary diagrams, when we are working with ternary diagrams and liquid extraction, the way we define our composition is in terms of weight fractions or weight percentages of one of the three components. So our system will be composed of A, which will be our solute, S, which is our solvent, and C, which is our carrier. And so a typical notation that we will come across in these systems will be something like this. So we'll have X sub A in phase C. And so what this tells us is the mass fraction of your solute A in your carrier phase. So now if we look at what a ternary diagram looks like, we will see something that looks like an equilateral triangle. And the way we use this equilateral triangle is we examine the distance between vertices for each point that resides within this triangle. And so what I mean by that is, so I will call this vertex here the solvent vertex, S. The top vertex will be A, the solute concentration or weight fraction, and then this bottom right vertex will be our carrier composition, C. And the way this ternary diagram works is that the farther away on this equilateral triangle we are from some vertex, the less of whatever component we are looking at there will be. And so examining this, as we travel down, as we travel down our equilateral triangle, regardless of whatever value to the left or right we have, we approach 0%, 0 weight percent A, and at the top vertex at this point here, we have 100% A. And the same can be said of the other vertices. So if we examine how our solvent weight fraction evolves with respect to the distance from this bottom left vertex, we will have 100% at the leftmost vertex and 0% everywhere along this side here. And so at this point, the next step we will do is draw a two-phase region within our ternary diagram. And this information is generally tabulated and it will be given to you on a problem set or on an exam because it changes based on variables such as pressure. So changing the pressure will change the size and the dimensions of this two-phase region that we are working with. But for the sake of continuing and keeping things general, on this two-phase diagram, I will pretend like we have a two-phase region that looks something like this. So everywhere in here will be the one-phase region, and everything in here will be the two-phase region. And what this means is within the drawing that we have above, every point inside of each one of our contact units that make up our total liquid-liquid extraction unit will exist somewhere within this two-phase region. And within this two-phase region, our system will have two phases, and each of those phases will have different compositions. And these compositions are tabulated, you will be given them, and with these values, we can draw things called tie lines. And these tie lines tell us how a particular solution will distribute itself amongst the two phases within this two-phase region. And so with these tie lines, we draw lines across them. And if I could draw better, these would be linear, but you get the idea. And so I will label these things I just drew as tie lines so people can follow. And we will proceed in how do we actually find the number of trays that we want or are needed for a particular system that we are evaluating graphically. And the next step that we will do is plot the points of the compositions that we know. And so we know that our solvent is pure, so we can label this point S, and we know that our feed will consist only of carrier and solute, so it must exist as some point on this AC line in our equilateral triangle. And so it will be, our feed can take on some point here, for example. And so this will be point F. And we will also be given the retentate value, the retentate composition exiting our nth tray. So that will be the third piece of information we know for our system. And the next step will be connecting the points SF to define a thing called a mixing point that makes the calculation for the number of trays we will need able to be calculated. So we will now turn to, okay, so if we now connect these 2 points, and I cheat a little bit with this line, what we see is we have the line SF generated, and if I could draw this a little bit nicer, I would, but for the sake of continuing, let's just assume these lines are all perfect and beautiful. What we now turn to is a mass balance, and this mass balance is something that you can find in a textbook, and it's a way we evaluate the mixing point in our system, and it tells us that the feed molar flow rate divided by the solvent molar flow rate is equivalent to the rate of the mass fraction of your solute at your mixing point minus the mass fraction of your solute in your solvent divided by the mass fraction of your solute in your feed minus the mass fraction of your solute in your mixing point. And your mixing point is a fictitious point. XAS is typically equal to 0 because it's a pure solvent. And because we know the feed flow rate, the solvent flow rate, and the feed composition of its solute, we can evaluate XAM because we have one equation with one unknown. Sorry. And so with XAM, we now know one of the 3 values we need to define the mixing point on our equilibrium triangle or our ternary diagram. And so what we now do is find where this XAM value will hit this SF line that we drew. And so let's say that we found XAM to have a value of 30. What this means is that we look across this 30% mass fraction line on our ternary diagram, and we see that it intersects our SF line here, and so this tells us that our mixing point in our system is right here. And so the next thing we will do is connect the R sub n point through our mixing point and figure out where this hits our left side of the two-phase region. And this point here will be equivalent to E1, which is the extract composition of our tray that of our first tray in our contact unit. For the sake of simplicity, I will now draw a new ternary plot so we can keep things a little bit cleaner so it's easier to follow. And I will make things very generic and perhaps a little bit sloppy, but I hope I can still convey the major concepts here. So with the values that we have just obtained from our mixing point, we now know our point E1. We know our solvent composition S. We know our retentate composition R sub n. And we know our feed composition F. And so what we are going to do next is connect the points SF and E1F to find something called a pivot point, P. I'm sorry, what I meant to say was we will actually connect SRN and the line SRN and the line E1F to evaluate our pivot point P, like so. So if we extend this line out, SRN, and we extend the line E1F, we'll find that they intersect at some point outside of our equilateral ternary diagram at point P. With this point P, we can now proceed to the next step of actually counting off the number of trays that will be needed in our system. Alternatively, another method of evaluating the pivot point P is based off the given data you'll commonly have from the tie lines. And if we evaluate the intersections of the tie lines, what we'll find is that the tie lines, if we extend our tie lines out, we'll have a tie line that hits our operating line SRN at a point farthest to the right. And whatever point this is your pivot point, not R, but rather P. And so continuing, once we have a pivot point and we have the other points in our diagram, we can now evaluate the number of trays that will be required. So we'll have some solvent point here. We'll have an R sub n value here. We will have our pivot point out here. And we will know a priori what our top tray composition will be. It will be E1. And so what we'll do is, and sometimes with these ternary diagrams there will be a bit of interpolation involved with the tie lines. What we'll assume is that, or what we know happens within our tray N, we have reached some kind of equilibrium, some two-phase equilibrium between our carrier phase and our solvent phase, and the tie lines tell us how this equilibrium, what these equilibrium compositions are. And so what we will pretend in this example is that we will have some kind of tie line that tells us what, so this will be En, coming in here will be your feed, exiting will be your retentate composition Rn. With these values, we will now know what the point En is. So our tie lines tell us how we move to the left. And we now use our pivot point to tell us the relationship between En and the incoming R sub n minus 1 quantity on the opposite side of our two-phase region in our plot. And to do that, we draw a fictitious line between E sub n and point P, and we see where this intersects our two-phase region in our ternary plot. This gives us a value R sub n minus 1. And then from this value R sub n minus 1, we now move to the left again. If we interpolated from a tie line, it would look something like this. And this tells us what the composition E sub n minus 1 is. And then we again extend E sub n minus 1 out to our pivot point to get R sub n minus 2. And from R sub n minus 2, we would assume our tie line would give us some value right here, which would have a value E sub n minus 2. And what we'll note now is that E sub n minus 2 has a greater mass fraction of our solute A, because this is our our solute vertex, than our required E1 term has, and therefore we can stop adding stages into our liquid-liquid extractor. And so the number of required stages is equal to the number of tie lines, the number of times we needed to hit equilibrium, that are in our system. And I'm sorry for being so messy with this stuff. Ternary diagrams are they can lead to inaccuracies, and it is very common in practice to use Aspen, but in introductory chemical engineering classes that discuss mass transfer and introduce the concepts of liquid-liquid extraction, this is how we evaluate things graphically. It's how we evaluated things before we had computers in Aspen. So being able to do this and understand the concepts involved is very important. And I hope you guys find this useful. Thank you for watching. Let me know if you have any questions.